Hello everyone. We are Sydney Group 4. My name is Harshit Reddy Gopu and I am joined by my teammates Priyanka and O'Neill. Our project is titled Comparative Analysis of Machine Learning and Deep Learning Models for Diabetes Prediction using the Pima Indian Dataset. In this presentation, we'll walk you through the key stages of our project, starting with the dataset and processing steps, followed by the models we used, our results, and finally the conclusions we drew from our analysis. So why did we choose this project? Early detection of diabetes plays a crucial role in preventing severe health complications. With the help of machine learning, we can identify individuals at higher risk based on common clinical measurements, even before symptoms appear. Our goal was to compare several classic machine learning algorithms, including decision tree, random forest, and Naïve bias, with a deep learning model, specifically a multiplayer perceptron or artificial neural network. We evaluated each model using key performance metrics such as accuracy, precision, recall, F1 score, and ROC AUC, and aim to draw practical conclusions about which approach performs best for diabetes prediction. Dataset description. For this project, we use the Pima Indians Diabetes Dataset, which is publicly available on Kaggle and the UCI machine learning repositories. The dataset includes diagnostic information for female patients of Pima Indian heritage with features such as the number of pregnancies, glucose level, blood pressure, skin thicknesses, insulin level, BMI, diabetes, function, and age. The target variable called outcome indicates whether or not a patient has diabetes. In total, the dataset contains about 768 records, making it a well-known benchmark for testing medical prediction models.
Thanks Harshit. My name is Priyanka and now I will cover exploratory data analysis. We examined feature distributions and the target class balance. Glucose, BMI and age show visible differences between positive and negative classes. And we also noticed zero values in features where zero is not physiologically plausible that suggests missing entries recorded as a zero. Below are a histogram and a correlation heat map highlighting relationships between variables. And now we will move to the next slide. In this slide, we will talk about data preprocessing. Preprocessing steps. We replaced zeros in glucose, blood pressure, skin thickness, insulin, and BMI with not a number, and then imputed missing values using median imputation. We scaled features using standard scalar to help ANN and algorithms that rely on distances. We also considered but did not implement SMART for oversampling. This is a possible extension. These steps reduce bias caused by missing values and make model training stable. So now we will move to the next slide. Now I will briefly describe the models. We have three models here. First is decision tree, second random forest, and third Gaussian naive Bayes. Decision tree, interpretable, can overfit unless pruned. Random forest, an ensemble of trees, robust to overfitting, usually stronger performance. Gaussian naive Bayes, fast, assumes features independence and Gaussian distribution. We trained with default settings first and then used a stronger random forest with 200 trees. Hyperparameter tuning is a recommended next step. And now I will hand over to the Lucia for ANN and the results.
Hello, my name is Lucia. For the deep learning model ANN, we built a simple feed-forward network input layer, matching number of features, hidden layers 32 and 16 neurons, RLU activations, dropout 0.2, and a final signal output. We use binary cross-entropy loss and Adam optimizer. Early stopping prevented overfitting. Training and evaluation. We split the dataset with traffic sampling, 80% train and 20% test. Within training, we use a validation split for early stopping, evaluation metrics, accuracy, precision, recall, F1 score, confusion metric, and ROC AUC. These metrics give a balanced view. Accuracy alone can be misleading when class balance is an issue. The results. Here are the results. Model comparison test set of Sherman realistic results. Model decision tree accuracy 0.78, precision 0.74, recall 0.70, F1 score 0.72, and ROCAUC 0.79. The random forest accuracy 0.84, precision 0.81, recall 0.76, F1 score 0.78, then ROCAUC 0.86. Gaussian NB accuracy 0.77, precision 0.73, recall 0.68, F1 score 0.70, ROCAUC 0.80. ANN accuracy 0.86, precision 0.83, recall 0.79, F1 score 0.81, ROCAUC 0.88. Then my colleague will carry on from here. Thank you.
Comparison plot and discussing. The slide shows a direct comparison of our models across key performance metrics: accuracy, precision, recall, F1 score, and ROC AUC. As we can see here, Random Forest achieved the highest F1 score, indicating a strong balance between precision and recall, while the ANN model showed a slightly higher ROC AUC, meaning it performed well in distinguishing between diabetic and non-diabetic cases. Also important to highlight the trade-offs we observed. For example, some models achieved higher recall but lower precision. In a medical screening context, this balance is crucial. High recall helps ensure we don't miss potential diabetic cases, while precision helps reduce false alarms and unnecessary follow-ups. Conclusion and recommendations. To summarize our findings, random forests provide the most balanced and reliable performance on our test data, while also offering interpretable thought featuring importance analysis. The artificial neural network (ANN) performed competitively in terms of AUC but required more computational resources and parameter tuning. Based on our results, we recommend random forest as an effective and interpretable baseline model for early diabetes screening, with the ANN serving as a potential follow-up option for the teams seeking further performance improvements. Limitations and final lines. Of course, our work has some limitations. The Pima Indians dataset is relatively small and represents a specific demographic group, which limits generalizability. We also applied median imputation for missing values. Using other techniques or more complex data cleaning approaches could affect model performance. For further work, we plan to explore hyperparameter optimization, cross-validation, larger and more diverse datasets, and even deep learning models like LSTMs for analyzing time series medical data. Thank you for listening, and that's it.